You have $35,000 in a savings account and decide to withdraw 20% of your money each year. Write a function that shows the balance of the account using negative exponents. Well, if you withdraw 20% each year and you continue to withdraw 20% of the remaining balance, that's exponential decay. So we're going to use an exponential model in this case. The general exponential model is f of x equals a b to the x. A is the initial amount, b is the decay factor in this case because, well, we're talking about decay. As a function of time, so I'm going to put f of t equals, the initial amount is 35,000, and then b is the decay factor. You're withdrawing 20%, which means 80% is remaining, so you want the balance, which is the remaining percent, so you're going to use the 0.80, and then to the t power. And remember the difference between the rate of decay and the decay factor. The rate of decay is 0.20, and the decay factor is what you repeatedly multiply by to create that pattern, and that's 1 minus the rate. So that's where the 0.8 comes from. Okay, so this is just the simple decay function. Now we're going to modify the function to use negative exponents. So we're going to use the exponential rule, the power to a power. And here's the thing. Let's say you have 1/2, and you want to write that as a negative exponent. Well, as a negative exponent, that's 2 to the negative 1 power. But how do you make that conversion? Well, what you can do is you can use the power to a power rule. So let's say you have 1/2 to the negative 1, and you put that whole thing to the negative 1 again. So basically you're doing a reciprocal and then another reciprocal. So if you do 1/2 to the negative 1, that's going to be equal to 2 over 1, then to the other negative 1 power. The negative 1 on the inside is used up, you still have the 1 on the outside. So you're going to have 2 over 1 to the negative 1, which is going to be simply 1/2. So using this power to a power rule to modify the way the 1/2 is written. It seems a little redundant, but let me show you in the actual function how it works. Okay, so what I'm going to do is I'm going to do 1 over 0.80, and that's the same thing as 0.80 to the negative 1 power. Then what I'm going to do is make the t negative. So what I did is I did the reciprocal of the 0.80 inside the parentheses, and then I'm saying with this negative power outside, I'm going to do the reciprocal again. So a reciprocal twice, which is really the same thing as this 0.80 in the first place. So you're doing reciprocal once, then twice. So then you may look at this and think, well, I don't know, what does this really say? I have 1 over 0.80 and then to the negative t power. This still doesn't make a whole lot of sense. Well, what I can do is simplify this 1 over 0.80 using the calculator. Then maybe it'll make a little more sense to you. Okay, so that's 1.25. So I can rewrite this function just like that. Okay, so what I'm saying is this f of t equals 35,000 times 1.25 to the negative t power is the exact same function as this one up here. F of t equals 35,000 times 0.8 to the positive t power. And all I did is use the rule of exponents to do a reciprocal, then another reciprocal, and that makes it have a negative exponent. So the next question might be, well, why would you do this? I mean, what's the difference? And really, it's all about just the way you think about it. I mean, with this first function, with the 0.80, you're repeatedly multiplying by 0.8. With this 1.25 to the negative t, you're repeatedly multiplying by 1 over 1.25 or dividing by 1.25. So do you want to think of it as repeated multiplication or repeated division? That's really the difference here.